Hello. Welcome everyone, including our online audience, to this week's Occupational and Environmental Hygiene Seminar. Today we have the pleasure of hearing from Dr. Sarah Henderson. So Dr. Henderson is an engineer and an epidemiologist. As a senior scientist at the BC Centre for Disease Control, she leads a program of applied research and surveillance in support of evidence-based environmental health policy for the province. As an assistant professor at the School of Population and Public Health, she supervises students in projects that further the BC CDC's mandate, and she teaches courses related to statistics and data analysis. Dr. Henderson has expertise in a wide range of environmental health content, including extreme weather, radon gas, food safety, water quality, and air pollution from multiple sources. Although diverse in scope, most of her work focuses on novel uses of large secondary datasets to address environmental health questions at the population scale. So please join me in welcoming Dr. Sarah Henderson today.
Thanks, everybody. I apologize to those of you in my class who have to listen to me for yet another hour. My preference would have been to have Chris Hong here at the front of the room. Chris was an undergraduate co-op student who worked with me for a year in statistics and computer science. And he's really responsible for most of these analyses and for a lot of the original thinking that went into this work. So I feel like a bit of an imposter standing here and speaking without him. But he is in class right now and he has a midterm, so he could not be here. Anyhow, today I'm going to talk about sources of air pollution that we don't necessarily hear too much about, especially in the kind of mainstream media. We get a lot of information about air pollution and global health risk associated with air pollution, but a lot of those pollution sources are both mobile sources and industrial sources. We don't talk too much about sources that are really quite important in British Columbia, which is residential wood smoke and road dust on paved roads. So all of this work that I'm going to talk to you about was done in partnership with the BC Ministry of Environment, where they came to the BC CDC and said, we have these data and we need to know some things from these data. Can you help us develop methods and tools to address these particular questions? So that's the framework for all of this. The study team, beyond myself and Chris Hong, included Arvind at the MOE, Gavin King at the MOE, Scott Weikenthal, who's at McGill, Mike, who we all know, helps with a lot of this, and again, the funding for this project came from the MOE. And I do want to say that all of this work I'm going to talk to you about got done on a relatively small amount of funding. It was basically Chris's co-op salary for a 1-year period. You guys know what a co-op salary is for a 4-month period, so multiply that by 3. And I think we got a lot of value for money out of this. So I'm just going to cover a very brief overview of air pollution and health. You guys should all have a relatively good foundation in this. I'm going to talk about residential wood smoke and road dust as sources in British Columbia, and then talk about 2 different projects. In the first of these projects, we were trying to develop an algorithm that could systematically identify smoky days using data that already existed. So very specifically, the PM 2.5 concentrations measured within communities and the temperatures measured in communities. We're looking at novel ways to combine those 2 sources of information to say whether or not any given day was impacted by residential wood smoke. The second study is around more specific to PM10 than to PM 2.5. The PM10 monitoring network in the province is aging. It uses instrumentation that's quite finicky to maintain, and the MOE is trying to make decisions about whether or not they want to keep that instrumentation going or whether or not we can retire it and look at PM 2.5 only. So just as a refresher for you, we're going to be talking about PM10 and PM 2.5. PM10 are particles less than 10 microns in aerodynamic diameter. Those are the blue dots on this little cartoon. So these guys, PM2.5 are the red dots, less than 2.5 microns in diameter. And then when we talk about the second study, we're going to be talking a lot about the coarse fraction. And the coarse fraction is the fraction of particulate matter that measures between 2.5 and 10 microns. So it's bigger than 2.5 and less than 10. We know particulate matter, or ambient particulate matter, is associated with human health impacts. I'm not going to go into that too much. I just want to give you a little bit of background information about how that relationship looks. So in this particular case, on the bottom here, we are looking at ambient concentrations of fine particulate matter, PM2.5, and then looking at measures of cause-specific mortality. This green line approximates the relationship between increasing PM2.5 and heart disease. This pink line approximates the relationship for lung disease. You can see this green line isn't really a line, it's more of a curve where the impacts for any given increase in PM2.5 are larger here for the small concentrations than they are for the large concentrations, whereas the pink line is sort of more linear. It's a linear relationship across. And then this dashed line is sort of the weighted average of those two lines. Now, if we cut the health impact in half here, so the maximum is at around 50, the minimum is around 0. When we draw a line at 25, you can see, oops, if you go and you move the slides in the right direction, the change from 2.5 micrograms per meter cubed to 5.8 micrograms per meter cubed has the same impact as the change from 150 micrograms per meter cubed to 25 micrograms per meter cubed in terms of the health effects that we can associate with PM2.5 concentrations within those ranges. So if we make relatively clean air even cleaner, we can have a bigger impact than if we make really dirty air similarly as clean. And that's important because we have pretty clean air here in British Columbia. This is our annual standard right now, 8 micrograms per meter cubed on average, so not very different from the 5.8 micrograms per meter cubed we're looking at in the minimum of this plot. But we do have lots of communities whose averages are higher than that, and a lot of those communities have higher averages because of residential wood smoke. So if we could improve air quality by reducing residential wood smoke emissions, we could have a pretty big impact on population health, even though the air quality in British Columbia is clean relative to global air quality. So when we're talking about anthropogenic sources of fine particulate matter, we all know about motor vehicles, and we all know about industry, and we all know about wood burning for heating. In all of these three categories, there's been really big technological improvements over the past few decades. Cars emit way less now than they used to. Controls on industrial emissions are far better than they used to be. And there's also wood stoves that can emit way less. The difference between these things is that for motor vehicles and for industries, there's strong laws and regulations in place that ensures that we use those best technologies, whereas the regulations around residential wood stoves are a bit different because we have to have individuals making those decisions. So even though we can restrict what wood stoves can be sold in stores from 2016 forward, we still have a whole bunch of people in the province who have older wood stoves. Sometimes these things could be 100 years old. They're not using the best technology. Unless those people go in and make the decision to buy a new stove to put in their house, they're still going to be using a highly polluting stove. And it's very hard for us to make people make that decision. It generally requires the municipal bylaws get passed, and then once the municipal bylaw is passed, it needs to be enforced. So it's a challenging thing to get people to move over to these new technologies. When we look at emissions for British Columbia that go into the National Emissions Registry or inventory, we can see for PM2.5, dust from paved roads and dust from unpaved roads are large sources. The next largest source is residential wood combustion. So even though a fairly small fraction of the province uses wood to solely heat their homes or to supplementary heat for their homes, the emissions are large, larger than all industrial emissions for the province, larger than emissions from all mobile sources. So fairly small percent of the population uses this, the emissions generated are large. Approaches to controlling those emissions. Like I said, we can restrict sales of wood stoves. We can say only the best technology can be sold in stores from this date forward, and we do that in British Columbia. We can implement exchange programs that incentivize people taking those 100-year-old stoves out of their homes and putting in one of these newer, more efficient stoves. We can also offer community education so that if people are burning wood, they are burning it as cleanly as possible. They're burning nice dried wood that's been cured for a couple of years. They know how to make a good fire, and they know how to make as little smoke as possible. Those are sort of the tools that we have available to us. Even so, the newer technology, although it is vastly improved over the older technology, burning wood still is going to generate quite a lot of emissions. The best possible way to burn wood is a pellet stove where the wood has been pelletized, it's nice and dry, it's uniform, you can get a nice uniform heat and low emissions. Next best way is an EPA certified stove. Even an EPA certified stove, if it's burning wet wood under poor burning conditions, it can still generate a lot more emissions than it looks like on paper when that stove is tested in the laboratory. So there's a lot of factors here that influence how much PM2.5 wood burning is going to create. So the challenges: lower emission stoves can still emit a lot. Wood stove exchange programs are quite expensive. We have to offer people money to change out their stoves. We have to administer a program like that. It can be challenging to do. Lots of people in BC in the Canadian context have burned wood traditionally. It's a nice cheap fuel source compared with hydro or other things, especially when prices in for those other sources become more unstable. And there's a sort of real hesitancy within BC and elsewhere in Canada, I think, to adopt more strict local regulations because of that factor. You know, people want to be able to burn wood, so a municipal government that comes in and says, you know what, you can't have wood stoves in the municipality anymore. Or you can only have them if you have a new stove that was manufactured after 2016. Those are very unpopular decisions to make. And encourage local municipalities and areas to make these decisions. They really want evidence basis for what the impacts of wood smoke is in their community. So you can know because you live in a certain place that it's smoky quite a lot, but that anecdotal information generally isn't good enough to motivate real change. So they want harder evidence. In terms of generating harder evidence about wood smoke and its impacts in any particular area, probably the gold standard kind of method is to measure levoglucosan concentrations. This is a byproduct of the pyrolysis of cellulose. So when temperatures are quite high, over 300 degrees, levoglucosan will get created when cellulose burns. And it's used as a pretty reliable tracer of wood smoke under ambient conditions. But generally, we've got to collect this stuff on a filter. We've got to send the filter to the lab. So it takes a special study and relatively expensive laboratory analyses if you want to do this over a long period to measure levoglucosan. It's kind of a boutique thing that would happen. We are also going to have to use fixed samplers if we want to do that rather than mobile sampling. Another possibility is mobile wood smoke monitoring. So this is a study that Mike did many, many years ago, and I still remember driving around very late at night or early in the morning looking for wood smoke across the lower mainland. So you've got a special instrument in a nephelometer and ethylometer that you put in a car, and then you drive around letting that measure continuously, and you can match those measurements up with GPS coordinates of where you actually were to make maps of where things were smoky. And this is the estimated wood smoke concentration map for our region. And at the same time they were doing that, they were also measuring this gold standard levoglucosan at some specific locations, and they compared the estimates that the map made of wood smoke with the levoglucosan estimates to see whether or not the wood smoke map was actually showing increased wood smoke. And indeed, there is a good, strong relationship there. And then finally, what we really want to be able to do is not have to do a special study, not have to use special equipment, but just rely on the data that we already have using new ways to look at it. So this particular visualization comes from colleagues in New Zealand, and I just want to take a moment to go over this with you. So along the bottom here, we have the months of the year, and they're set out so that the winter months are in the middle, and the summer months are at the side. And then here we've got the hours of the day. And with what happens with wood smoke is, you get in the morning, you put some wood on the stove, you generate some smoke. Generally, most people go out for the day. They're not heating the home while they're out. There's less wood being used, and then they come back and they ramp up the fire again, and there's more emissions again. At the same time, there's changes happening in the atmosphere where, as the Earth cools, the boundary layer comes down, and then as the Earth warms again, the boundary layer goes back up. So there's different mixing properties for the smoke that's in the air. What we expect to see in a smoky place is exactly what we see here. More PM2.5 in the nighttime hours and the morning hours as the months get cooler. So that sort of hourglass-shaped figure, that's the kind of information that would tell us this is a wood smoke affected place. We want to use the kind of information that was put into this to systematically look at all of the areas in BC where PM2.5 is measured and to rank communities with respect to their relative smokiness. A, so that we can generate a little bit more information about what the impacts are in the province, and B, so that we can better communicate with the communities about what the impacts are locally. So given that wood smoke sampling is too expensive to conduct in all affected communities of BC, and that communities want empirical evidence to inform local policy, can we reuse routinely collected PM2.5 and temperature data to assess wood smoke impacts in BC communities? This is the challenge that was set before us by the Ministry of Environment. The data that we have to work with here are concentrations, measured hourly PM2.5 concentrations, and temperature measurements in 23 communities. We excluded the lower mainland from this analysis, but you can see all of the communities listed there. And very, very fortunately, we were able to piggyback on work that Scott Weichenthal was already doing in Prince George, Kamloops, and Courtenay, where he had studies that had lasted a couple of years, and every day during those studies, they had measured levoglucosan concentrations in these 3 communities. So we have a bit of information about that gold standard. So, wood burning appliance use, as I described earlier. Actually, let's step back here. So there's 3 different things that we're interested in looking at. Temperatures, variability in hourly PM2.5 concentrations, and then information that might help to capture this diurnal cycle in the planetary boundary layer which is going to compare nighttime PM2.5 concentrations with daytime PM2.5 concentrations. So when it comes to temperature, that's fairly self-explanatory. The colder things are, the more likely people are to use their stoves. When it comes to variability in the 1 hour temperatures, again, we're expecting people to be using their stoves most in the morning and in the evening, with less use during the middle of the day. So we're going to expect high variability hour to hour in the daytime temperatures. Finally, this question of temperature inversions. So what happens is at night, we get often these inversion kind of conditions, especially in the mountainous and coastal areas of British Columbia, where colder air gets trapped close to the surface and it can't break its way out. So generally air is warm and it rises until it can't rise anymore, but if you have this layer of higher temperatures over this layer of lower temperatures, that can't happen and you don't get good mixing. So we are going to look at the daytime to nighttime PM2.5 ratio to try to evaluate on days where that ratio is 1.0, you know, that might not be as smoky as a day as when those ratios are lower. So we got to classify these three criteria: mean daily temperatures, standard deviation of the 1 hour PM2.5 concentrations, and the daytime to nighttime ratio. The question is, for these values of X, Y, and Z, what are the optimal values to choose for this algorithm, where we want to call a day smoky if the temperature is less than or equal to a certain value, if the variability is higher than or equal to a certain value, and if the daytime to nighttime ratio is less than a certain value. What should those three certain values be? And this is where those levoglucosan data come in really handy. So these are the levoglucosan concentrations, or the levoglucosan percentages. So they collected PM2.5 and then calculated how much of that PM2.5 was levoglucosan. So anywhere between 0 and 30%. These are the values for those three different communities. And you can see from this, Courtney is quite a different kettle of fish than Kamloops and Prince George. The air in Courtney is quite a lot smokier than the air measured in those places. So we said we are going to use the data from Courtney to help inform the decisions about these X, Y, and Z values. Here we've got the distribution of mean daytime temperatures on high levoglucosan days and low levoglucosan days. Do the means of these distributions look different, my class? What does your gut instinct tell you? Yes, they are quite different. So really, you can see when it's colder outside, things get smokier. When it's warmer outside, less smoky. So we look at the point that maximizes the smoky days while minimizing the less smoky days. And we say, okay, at a mean temperature of 13 degrees, we start seeing the most possible separation between these distributions. But then we look at a range of values around that as well to test the sensitivity of the algorithm to these decisions. This is the standard deviations of hourly values on smoky days, or days with more than 1% levoglucosan, and less smoky days. Again, we've got two distributions that really don't look much like each other, correct? So again, that value here gets drawn at a standard deviation of 3, but we look at a range of 2 through to 6. Just to ensure that we're testing a wide range of values. And finally, this is the one where the distributions are the most similar, but they're still not the same thing statistically. They are different from one another. And this is the daytime to nighttime ratio in the smoky days versus the non-smoky days. And you can see that the ratio comes down for the smoky days. So we chose a value of 0.05 and then tested that range within the gray bar. So for the values of X, Y, and Z, we chose 13, 3, and 0.5. These are the results in this line here. I should be showing this. I tell people this all the time. Oh my God. These are the results for that combination of values. And here, the communities are ranked by their order for this set of results. So this is sort of the base case, and all of these other ones are sensitivity analyses around that. Houston comes up as the smokiest community regardless of what values we use. Kamloops comes up as pretty much the least smoky community regardless of what values we use. And here you can see that there's relatively good consistency across all of the different values that we tested. So in general, these communities are smokier, and in general, these communities are less smoky. We found in Houston that 44% of all days, that includes both summer and winter, were impacted by residential wood smoke. In Courtenay, it was 29%. In Port Alberni, it was more like 21%. Lots of smoke in these communities, whereas in Kamloops, it was more like 3%. Here's that visualization again, applied to each community in their ranked order from our algorithm. So Houston, the smokiest community, it's got that hourglass figure that we're looking for. Courtenay's got it. Port Alberni's got it. Vanderhoof doesn't have quite such a nice tucked-in waist. Whistler's got it. Castlegar's got it. And in these smoky communities, the ones that were in the top half of that plot, we see this pattern. And then as we get into the bottom half of the plot, we start losing that hourglass figure. So we're using this as evidence to support the fact that, or the hypothesis that our algorithm actually does a pretty good job of at least separating smokier communities from less smoky communities. You'll see this banding in some of these plots, and that's going to be most likely, we took out forest fires from this, but that's most likely going to be pile burning in the shoulder season. So you can see it usually happens in the shoulder months. This was used as evidence to inform what Matt Wagstaff is currently doing. So we haven't seen Matt around very much recently, and that's because he's been out doing a mobile monitoring study and measuring levoglucosan in 3 of the communities that we identified to be most smoky. So he's been looking at Courtenay and a smaller community outside of Courtenay where we don't have any measurements. He's been looking at Vanderhoof and at Whistler. So far, he's just back from Courtenay and he's heading up to Vanderhoof next week. And this is the kind of data that he's collecting, similar to that study that I showed you earlier for the Lower Mainland. He's driving around a new type of instrument that has 2 different channels, and when we look at those 2 channels together, it gives us a really specific wood smoke signal, as opposed to the instrument that Mike used in his study, which was more general. And so where you see red, we're saying that's probably a much smokier place than where you see yellow. So this is Courtenay, and that little community is called Cumberland. Here's a zooming in of Cumberland. So that's how much variability there can be spatially within a relatively small area. So in Courtenay, for example, the monitor that we used to make our estimates was right here. But there's definitely smokier places around Courtenay, and the smoke in those neighborhoods might not be well reflected by the monitor. And then this is the same for Whistler. So you can see You know, it's highly spatially variable. I won't go, I'm sure we're going to get Matt to do this at some time next year, so I won't ruin any more of the details of his study. So overall, we feel that the algorithm does a pretty good job of at least separating smoky communities from non-smoky communities, and to some degree evaluating the relative smokiness within communities. We think what we've done here could probably be applicable to other high-income countries that are also affected by wood smoke. This is not a uniquely Canadian problem. It happens in the US, happens in Australia, happens in New Zealand, happens in Europe. So we hope that others can use these methods to their advantage. And perhaps most importantly, it allows us to more carefully target further research at communities where we know the impacts are likely large. So, you know, this really helped us. I don't think, without this work, I don't think we would have identified Whistler, for example, as among the more smoky communities in the province. I mean, we kind of knew that Castlegar was a problem. Like, we know, again, anecdotally, that some of these places are wood smoke impacted, but other ones were kind of a surprise to us. Now, we switch to road dust. So, road dust. In different contexts. First of all, we have unpaved roads. Heavy machinery tends to move along them for logging or mining or other resource extraction in the province. They can generate quite a lot of dust, especially in the summer months when things are really dry. Generally speaking, this dust does not affect populated areas. These things are far removed from populations that might be exposed. On the other hand, we have road dust on paved roads, which is more specifically a springtime problem. So over the course of the winter, traction material gets laid down, salt gets laid down, all of the oil and brake wear that comes off of cars all the time gets stuck in with the snow or under the snow. And then when the snow starts to melt under dry conditions, we get really dusty days around roads. And it can look like this. It can be awful. Has anybody been under road dust conditions? You can taste it. It's pretty gross. Yeah. And we do have a lot of air quality advisories across the province, especially at this time of year, February, March, where dust is really kind of getting kicked up everywhere and is hanging around. A lot of this stuff happens on highways, so if you go back to my emissions for the province, you know, there's a lot of highway where this dust is getting kicked up, but there isn't necessarily people living there, but it also affects communities. So the measurement technology that we use for PM 2.5 and PM 10 has evolved somewhat over the past years. What we used to use is called a tapered element oscillating microbalance, and it's a pretty finicky instrument because it's kind of weighing PM all of the time. We initially started measuring PM 10 with these instruments, and then we started measuring PM 2.5 with these instruments, and then over recent years we've been switching out the PM 2.5 TOMs for beta attenuation monitors, and this is collecting the air onto a filter tape and then shining beta at the filter tape and measuring how much is returned. So it's a much easier, simpler, more stable type of instrument. So all of the province pretty much has been converted to these BAMs now for PM 2.5, but the PM 10 TOMs are still kicking around, and they're aging, and keeping them working is a labor of love to some degree. So the question is, do we keep trying to keep these things working? Do we actually need PM 10 measurements? We know that PM 2.5 is sort of more harmful to human health than PM 10 is. What do we do here, and what information can we have to inform this decision? And for the most part in BC, you know, when we're talking about PM 10, the biggest health risk that we're concerned about is that road dust. So given that PM 2.5 is more harmful to human health and the provincial PM 10 network is aging, what evidence is there for continued monitoring of PM 10 in BC? This, again, is the question posed to us by the Ministry of Environment. In this case, we are looking at data at the local health area level. So local health area is the smallest health geography in BC, and we are looking specifically at communities or local health areas in the interior with at least 10,000 people living in them. So when we apply those restrictions, as well as the community having at least 3 years of overlapping PM10 and PM2.5 data, because here we want to calculate the coarse fraction, we end up with these 7 local health areas. This is what the time series of data looks like for each of these local health areas. They are sorted here according to their population size. So you can see the dark line is PM10 measurements, the lighter line is PM2.5, then we have temperature, relative humidity, and we've defined an influenza season for the analyses. We are going to look at the relationships between PM2.5. Let me step back here. We're going to use 3 different measures of particulate matter. One is PM2.5, one is PM10, and one is the coarse fraction, or the difference between them. In all cases, we are only using data from T-ohms for these analyses. We did not include the data from the BAMs. We want to evaluate how each of those particulate matter metrics is associated with 2 different indicators of population health. One of them is dispensations of salbutamol sulfate, which is Ventolin. So anybody who's got a reactive respiratory condition is going to have this on hand as a rescue medication. So we look at those, and then we look at non-accidental mortality. And in looking at these 2 outcomes, we're kind of spanning the spectrum of stuff that can happen. Having a little bit of difficulty breathing and needing to use a rescue medication is mild in the scheme of things. Death is about as severe as it gets. Here we have the number of days that each of these communities contributed to the analysis, where we had overlap between all of those sources of data. Road dust is not the only source of PM2.5 in these communities. There's all kinds of other sources. So we've got mobile sources kicking around, we've got residential wood smoke, we've got construction, which is a huge source of PM for the province, we've got industry, we've got forest fires, and we have resource extraction and mining. So there's all sorts of other things that are contributing to the particulate matter in any given region. We can't do a lot to control for that in the data that we have. PM10 is PM10 is PM10, comes from whatever sources it comes from, but we can stratify our analyses seasonally to sort of look at these things a little bit better. We know that road dust is a problem in the spring, February, March, April. We know that residential wood smoke is going to be a problem through the winter months when it's colder. We know that forest fires are generally going to happen in the summer. So if we can break our analyses up by year, we can at least start looking at some of these seasonal differences. This is a similar type of heat map to what you saw earlier, showing PM2.5 over the year for each of these communities or each of these local health areas in the analysis. In this case, we are starting in January and ending in December. You can see PM2.5 concentrations are generally higher November, December, January, February. That's going to be from your residential wood smoke. You can see they're generally highest in August. That's going to be the signal from your forest fires. When we look at the same thing for PM10, we can see that high PM10 is sort of concentrated in January, March, and April. There's your road dust season, your paved road dust season. And then when we look at the coarse fraction, again, we see it as highest in these 3 months. So what we did is cut up the analyses into the residential wood smoke season, which we called October to January, the wildfire season, which we called July and August, and the road dust season, which we called March and April. We left February out of these analyses because it has both high PM2.5 from residential wood smoke and high PM10 from road dust. And we wanted to be able to better tease apart those two things. This is a big plot. I'll try my best to walk you through it. First of all, we are looking at relative rates here on the y-axis. So this is a 10% increase in the rate of salbutamol dispensations. Along the x-axis, we have each of the communities, and then at the end, we have a meta-analysis estimate that takes the estimates for each of the communities and pools them. The triangles show the winter months, the circles show the spring months, and the squares show the wildfire months. So what we can see up here, PM10 associated most strongly with salbutamol dispensations during the summer wildfire months. And when we look at the meta-analysis estimate, note that this y-axis has changed. We see about a 5% increase in salbutamol dispensation rates for a 10 microgram per meter cubed increased change in PM10. We see about the same thing here for PM2.5. Now remember, PM10 as measured here does include PM2.5, so that's not very surprising. And then when we look at the coarse fraction, oh, we see the same thing. One concern here is that the coarse fraction can still be confounded by the fine fraction, because it's still going to be high on days when PM2.5 is high. So the best possible way to do this type of analysis is to adjust this effect even further for the PM2.5 effect. So now we've got a multiple linear regression model with two variables in it. One of them is the coarse fraction and one of them is the fine fraction. And when we do that, we see no significant association. So that completely attenuates the effect of the coarse fraction. When we look at non-accidental mortality, it's a slightly different story. So, same deal here. We're still looking at increases in mortality. We're still talking about 10 microgram per meter cubed changes in the PM metrics. Here we see no association in the winter months. We see association in the spring road dust season and some association in the summer months. When we look at PM2.5 alone, similar sort of story, more extreme effect estimates. And then when we look at the coarse fraction, still nothing in the summer months, about a 4% increase in mortality for every 10 microgram per meter cubed change in the coarse fraction, and even higher in the summer months, although the confidence intervals are quite wide, and they do cross 0 here. When we adjust these effects for the fine fraction, so here's the crude effects, here's the adjusted effects, unlike with the salbutamol dispensation, this doesn't go away. So the coarse fraction, even when adjusted for the fine fraction, is significantly associated with increased mortality during the winter or the spring road dust season, not significantly associated during the summer forest fire season. But remember what I said earlier on, summer is also the time at which roads are dry. So we get road dust in summer from that. It's a slightly different kind of road dust because it doesn't have all of that crap that came with the springtime road dust, the traction material, the salt, the brake wear, the oil. So there might be slightly different types of road dust, but it still can be dusty in summer. Finally, we do a sensitivity analysis where we take every community out of the meta-regression estimate to see whether or not that community had a lot of influence on the meta-regression estimate. So if a community didn't have a lot of influence, we expect the meta-regression estimate to remain stable, whether or not it's in or out of the analyses. So here's the overall estimate, and here's the meta-regression estimates for each community missing. So when we remove Smithers, this stays about the same as this. This stays about the same as this. And that's true pretty much across the board. There's no particular community that is unduly influencing this coarse fraction estimate during the road dust season. However, when we look at the summer season, when we take Vernon out, this comes down quite a lot. So we've got evidence here to say that actually what's happening in Vernon is really kind of driving the whole estimate, whereas we don't have any particular community driving this estimate for the road dust season. So, overall summary, PM 2.5 was associated with salbutamol dispensations during the summer forest fire smoke season. Not the coarse fraction, the fine fraction alone. This isn't surprising to us. We've done a lot of work on PM 2.5 from forest fire smoke. We knew and expected that salbutamol response. The coarse fraction was associated with non-accidental mortality during the spring road dust season. And that association remained even after we adjusted for the fine fraction. It was a robust association. The coarse fraction was also associated, less so, with non-accidental mortality during the summer season, but that association seemed to be driven by the relationship in only one of the 7 communities, and that was in Vernon. We did not observe any relationships between our particulate matter metrics and either of these health outcomes during the winter months, where we expect residential wood smoke to be the source of interest. But I want to point out that of these 7 communities, only one of them was ranked as a smoky community by our Woodsmoke algorithm. The other 7 were in the less smoky communities. So it could be that residential wood smoke just isn't as much of a factor in these particular communities that are affected by springtime road dust. All of this we put together to recommend that the Ministry of Environment would be best if they could continue measuring PM10 in communities where we know springtime road dust is an issue. There's a fairly strong relationship there. A 3% increase in mortality is, in the scheme of environmental health measures, measurable and fairly large. So we do want to be able to keep continuing to issue road dust advisories based on measurements of PM10. So whether that means keeping the old network going as a labor of love or investing in new instrumentation for PM10, similar to the instrumentation that's been introduced for PM 2.5, that's for the ministry to decide. But out of this, we do recommend that the province continue to measure PM10 in places where road dust is a known factor. So thank you very much for your time, and happy to take any questions.
Thank you, Dr. Henderson, for that interesting presentation. Any questions?
Thanks, Sarah. That was really interesting, especially because I hear a lot about this work, but seeing all the visualizations really brought it home for me. I was wondering, because you mentioned this relationship between inversion and both coastal proximity and topography, if those were other factors that you thought other locations might want to include to refine the daytime, nighttime temperature difference in their models.
Yeah, so I think there's probably quite a few other variables that could go into that type of algorithm to help, and we did sort of think about coastal proximity or, average elevation change over the area as other possible indicators. So I think there's a lot of room for all types of refinements, but that would be one of the things to consider.
So thanks. I hadn't seen the road dust stuff. That's really interesting. And I guess a question on your Woodsmoke and your summer forest fire. So a couple things that I guess are different. One is that in winter people are inside and houses are closed up, and in summer, so that may be explaining it. But I guess the other thing is you could also identify where forest fires are. So have you done that to sort of rule out whether this is
so what I didn't mention is I did say in these analyses, most of these communities were ranked among the less smoky from our other study. In previous studies, we've also broken all of the local health areas in the province up into those that are routinely forest fire impacted and those that are not routinely forest fire impacted, and all of these 7 communities are in the routinely impacted group. So we didn't look specifically at individual fires or individual fire seasons within these analyses, but we do know in general that those local health areas do experience forest fire smoke in summer.
And I guess just a follow-up, just trying to tease apart, that summer signal, whether it is fire or dust. So you could imagine that it would be dust and it would have a higher effect because people are outside.
Yep.
I'm imagining there's probably, I'm not sure how sensitive it would be, but you could look at kind of road surfaces, how many gravel roads versus paved roads kind of in the area. Have you?
Yeah, that would be a really good idea, because we do expect dry dust from both paved roads and unpaved roads, but obviously if there's a lot of unpaved roads in an area, that dry dust might be a bigger factor. So that's a good suggestion. Thanks, Mike.
Hey, Sarah. So I just want to clarify the hourglass slide that you had.
You want me to go back to it?
Yeah, if you don't mind. And if you could just re-explain that to me, because I kind of missed it, the idea of having that band that shows, and you explained that it was related. So when you had all this, so the hourglass is how we are able to say, yes, it is a smoky area. And then you have, you look at Burns Lake, where somewhere you have that one strip that shows.
Yep.
Right after the, yeah. And then we have it again in Squamish, but this time it's more in the winter than, right? You see the, yeah.
Yep.
No, it's not Squamish, it's number 14, Grand Forks. So you have it this place. So what's going on there?
So we don't exactly know because we aren't there watching what's happening, but our best guess, especially for a band like this, which is happening in February or March of every year, is that this is pile burning. So, if there's waste wood piles sitting around the province, we can't burn those in the summer because there's too much forest fire risk. So you got to burn them when it's still relatively cool, but the venting conditions are good enough that you're able to burn. So generally this burning happens in the spring and in the fall, rather than in the winter or in the summer. So I'm guessing that around Burns Lake, this is a pretty normal time to get those piles burned off. In Grand Forks, here we've got this in August. It could be we didn't do a great job of stripping out the forest fire signal for Grand Forks. We only removed the 99th percentile of PM 2.5 values in summer. That was sort of our course cut for getting rid of forest fires. So I'm going to guess that that is forest fire related, but that this is shoulder burning. No worries.
All right, we have some online questions. So one question was just wondering if you considered and controlled for pollen, given that this is usually also highest in the spring and linked to asthma response.
Pollen. So that's an excellent question. It would be lovely to be able to consider and adjust these analyses for pollen. We don't have really good pollen data in Canada. So pollen are collected at about 20 stations across the country, certainly not collected at this resolution in British Columbia, and those data are not particularly readily available. So I would love to if we could, but they just don't have the data.
Okay. We have just one or two more. No. One question was just curious to know why you outlined the influenza season as well.
So because we were looking at non-accidental mortality during, March, April, that sort of winter coming into spring months, that's also the time of year when influenza epidemics happen, and we didn't want to accidentally pick up influenza deaths. We didn't want to accidentally say that PM 2.5 was associated with influenza deaths, so we didn't strip those days out of the analysis, but we controlled for them to say this was a day when influenza deaths were high.
This other listener said, I heard that PM 0.3 is a new concern due to its direct effects on the brain. Are there any studies from UBC or BC CDC around that?
So Mike is probably better off answering this question than me, but I'll give it my best shot. So now we're talking about particles in the ultrafine category, so very, very, very tiny particles if you go back and think about that slide with the hair. And those particles are generally, they can be produced by a lot of different processes, but certainly forest fire smoke would generate particles in that category, or residential wood smoke. There's emerging evidence around these really small particles and what their human health impacts may be. We can't do studies like this with those measurements at this point because it's not something that the Ministry of Environment measures. And I think there's probably a lot of interest growing in BC and in Canada about if we're going to measure these things, how are we going to do it? How best is it to do? But I think one of the concerns is that they vary so spatially that, a centralized monitor like the one on the roof of a station in Courtenay really isn't going to provide very valuable information about what the actual exposure of that population is to those particles. Whereas, for PM 2.5 or PM 10, those background measurements are more useful.
I had a question about the salbutamol dispensation.
Yep.
Do you think healthcare access could play a role in the readings that you got for that?
Yeah, probably. So, one thing to think about here is we're counting dispensations on any given day. That's not necessarily uses, but we're making the assumption that if people are going to the pharmacy to fulfill their Ventolin prescriptions, that they're using their Ventolin and they've run out, or that they're close to running out. So to get a prescription for Ventolin, you do need to have one from a physician, and if you're out of your, generally you have a standing sort of prescription that you need to have refreshed every year or every 6 months. But if you haven't been able to make it to your doctor to get your prescription refilled or renewed, then there might be an issue with that. It's not a great measure of what's actually happening in the population. It's just an indicator that we can use.
Thank you.
Okay, there's one more online question. Not sure if you can answer this, but Whitehorse is located in a deep river valley surrounded by cliffs composed of fine river sediment, clay, and sand. Would this material be comparable to road dust?
I mean, in terms of size fraction, yes, but in terms of its constituents, No, likely not. Especially that sort of, again, that springtime road dust that we're talking about, where there's all those different things that are part of that dust. So it's not to say that there shouldn't be no concern about more sort of natural crustal material and dust from those materials. Same thing with sea salt. It's in that fraction, but I wouldn't consider them to be the same exposure.
Okay, so that is all the time we have today. Thank you for everyone who attended in person and online.